In this video, we're going to find an absolute extreme value that has an application here for minimum distance. So we have the surface y squared equals 9 plus xz. We want to find the points on this function that are closest to the origin. So we're going to minimize distance to the origin. Well, distance has the distance function has a square root in it, but if we minimize the square of the distance, that's the same thing as minimizing the distance. So for convenience sake, we will minimize the square of the distance, which will be x squared plus y squared plus z squared. But again, this point, this y squared has to be equal to the 9 plus xz because we have to be on the surface. So we replace the y squared with 9 plus xz. This is going to be our function of two variables now. Take our first partials with respect to x and with respect to z. We get 2x plus z for our partial with respect to x plus 2z for our partial with respect to y. We see that these are simultaneously 0 when both x and z are 0, and that's it. If you were to solve that system of equations, setting them both equal to 0 and solving, you would get 0 for both x and y. Oh, excuse me, x and z, my apologies. So, take our second partials with respect to x, mix second partial, and our second partial with respect to z. We get 2, 1, and 2, respectively. So then when you calculate the d value, no matter what point you're at, but in particular at the 0, 0 point for x and z, we get 3. So since the d is positive and the a is positive, this critical number yields an absolute minimum. Or excuse me, it yields a local minimum. And certainly, the bigger the x and the z's get, d squared is going to get bigger. So this has to be an absolute minimum value that we're getting out. If we put in x equal to 0 and z equal to 0, we get y squared equals 9. So our y equals plus or minus 3. So the points on the surface y squared equals 9 plus xz that are closest to the origin will be 0 plus or minus 3, 0.